Okay, we're going to do a quick run through of this slideshow, and it may seem a little bit like it's a little hard to string together in the beginning. It starts with a discussion about chemical bonding and energy transfer. It goes then into how to write thermochemical equations, and then finally into potential energy diagrams. So a couple of things that we need to discuss very quickly. First things first is that chemical reactions, just like physical changes, can be endothermic and exothermic. Ultimately, all of the reactions that we're going to discuss still have to follow the laws of thermodynamics. Since this is the point where we're going to talk about heat and energy transfer for chemical reactions, that's the full amount of the material. Most people teach it with physical change and chemical change together. I do them separately so that we get a chance to come back and learn it a second time, so that hopefully the repetition helps you really get the information down pat. So the first thing that we have to talk about is the contrast. So there's a contrast between physical change and chemical change. So first, let's go back to the energy and phase change slideshow from Q1. In that slideshow, we talked about how energy moves in or out of physical systems. And we talked about how when something is going from the surroundings into the system, that's endothermic. And if it's going from the system into surroundings, that's exothermic. Now, for a physical phase change, though, when you've got energy moving in or out, all you really are doing is moving the particles more or less. Okay, so you're either increasing their kinetic energy or decreasing their kinetic energy, and you're making them possibly change phase. Remember, change phase, change state just means you're going from a solid to a liquid or a liquid to a gas. You're not doing anything chemical there. That's all physical change. Okay, so if we were to go back to our discussion about different types of energy, when we do physical stuff, we're talking about mechanical energy, like shaking something, stirring something, pushing something, or thermal energy. You're just moving heat into something or moving heat out of it, but you haven't changed its identity fundamentally. Like if you're boiling water, it's still water. If it evaporates, it's still water, it's just in a gas form. If it freezes, it's still water, it's just a solid. What we need to move to when we do this unit is we actually have to start to talk about what happens in a chemical reaction. So now we're dealing with that chemical energy. Still to come, next quarter is nuclear energy, and then a little bit electromagnetic energy, and then fourth quarter is electrical energy. So we do actually get to all six of these. These are not the only types of energy in the universe. These are just the ones that we're going to talk about in chemistry that we're going to focus in on. So let's get back to the actual discussion about what's going on with chemical reactions. A few things you really have to nail down here. That is your idea about what a bond is. A bond is when two atoms chemically attach to each other. Now, a bond is much more difficult to break and accomplish. It's not, well, I wouldn't say it's difficult to accomplish. It's difficult to undo, much more than a physical change. Chemical bonding also absorbs energy and releases energy. But now you really have to think about this as a different thing than a physical change. In a physical change, energy is just making particles either move more or move less. In a chemical change, this attachment of atoms to each other can actually cause them to either decrease in energy or increase in energy. And that energy doesn't really make the particles move more or less. What it really does is it gets actually stored in between the atoms. So when we put fire in the category of chemical change, right, we get a lot of energy by burning things. Burning things is one of the ways that we get chemical bonds to break, and we get the energy out of those chemical bonds, and we convert it into heat so we can actually use it to stay warm. So this is fundamentally different, right? When you're trying to think about whether or not something is or exothermic in a physical change, you can make a prediction. In chemical changes, you cannot. And that is because each chemical reaction is going to do something different depending on what those atoms want to do. It depends on their chemical nature. It depends on that type of reaction. It might depend on the circumstances of how the reaction occurs. A lot of times it mostly depends on the elements themselves, but it can depend on the conditions. So in general, we're going to talk about some general rules first. In general, if you're dealing with covalent bonding between non-metals, there's a general rule that if you make a bond, the people going into that reaction probably have too much energy to start out with, and they would like to be more stable. So they will give up some of their excess energy when they make up this bond. And so forming a bond releases energy. If you then want to break up that party, right? You have two people who are now more stable as a compound, and they would rather be together, and you would like to break them up. You're gonna have to put some energy into that. They don't want to let go of each other. So if you want to break a bond, particularly covalent bonds, you're gonna have to input energy. And so we say breaking bonds absorbs energy. Now, looking at this middle part of this slide at the lower energy, right? Some very reactive elements are much happier when they are bonded. Okay, so often the most reactive elements will form the most stable compounds. Now, not every single one of those reactions will actually give off energy, though. We're talking mostly about the covalent ones. So some of the ionic ones will actually absorb energy when they make bonds, even though they're very, very reactive elements to start with. So a good example of a covalent one would be like two halogens making a bond, like iodine and iodine forming I2, or chlorine and chlorine forming Cl2. And those are the examples they like to use on the reagents quite a bit. All right. So reactions can be endothermic and exothermic, but it's not going to be like when we did physical change. When we did physical change, you could kind of think your way through, is this going to be endothermic or exothermic? Each reaction actually does its own thing, and that has to be studied by chemists, and you have to look it up on a table. There's no way for you to just look at a chemical reaction and be like, yeah, that'd be exothermic. It actually has to be tested. So I want to introduce you to your newest reference table. This is table I. Table I, say hi, table I. My terrible rhymes. I apologize, you guys. When you are using table I, a couple of things that you need to know. First off, that energy that's being given off is listed here on the right-hand side under delta H. I'm going to explain in a minute what delta H means. There is a list of different reactions. So if a multiple choice question, for example, asks you about a reaction and you're like, I don't know, how would I know? You're not supposed to know. It's on table I. That's what it is. Sometimes they'll tell you to look it up. A lot of times they won't. So we're going to go down to the bottom of table I. There's some reactions in here, though, that you are familiar with. Right, so here's the reaction to break salt into pieces. That's endothermic. Do I have the reaction for putting salt together? Weird. All right, here's the reaction for breaking up ammonium chloride. This is actually the chemical that's in those chemical ice packs. Or ammonium nitrate. It's one of these two, ammonium nitrate or ammonium chloride. You can see that these are both positive and these are negative. Right, here's the reaction for making water out of ions, not out of gas. So some of these have minuses in front of them, some of these have pluses, some of these have very big minuses. Right, here's hydrogen, oxygen are two reactive elements making water that's highly exothermic. These guys are very reactive on their own. They give off a lot of energy when they make this compound, but they make water, and water is way more stable than they are when they're by themselves. So, a few couple little notes down here I want to point out to you for when you're in the middle of a test and you're nervous. First, they tell you right at the bottom of the table that a minus sign indicates that a reaction is exothermic. So you don't actually have to remember it. If the minus signs are exothermic, then the plus signs must be endothermic. Yes, because there's only two categories, endo and exo. Okay, the other one is this little asterisk, which says that the delta H values are based on molar quantities represented in the equations. Let's go back to our water equation for a sec so we can talk about what the heck that means. Because they will bring it up at weird random times during Regents questions. Molar means that this quantity is in proportion to this recipe. So this is the balanced equation for making water out of hydrogen and oxygen. You probably recognize it at this point in the game. Right? You guys have seen this equation multiple times. You've balanced this equation multiple times. Okay. You know that this is the correct balanced equation. This is how much energy this reaction makes at these quantities. That's what that means, molar quantities. It's proportional to how much is being made in this equation. Okay. So that means that if you were to double this, you would make twice as much heat. If you were to cut this in half, you'd make half as much heat. So it's proportional to the equation. If you're already okay with your stoichiometry and what I mean when I keep saying proportional over and over again, you'll probably get what I'm saying. If not, you probably need to come see me, because if your stoichiometry is weak, the rest of this is not going to go that well for you. All right, let's dig into the rest of thermochemical equations, etc. Okay, now there's are some general rules, right? Breaking bonds absorbs energy, and forming bonds releases energy. That's not true for every single reaction. So if it's a specific reaction, you may need to look it up on table I. They might tell you in the question. All right, let's talk about the laws of thermodynamics very quickly, because we are in the realm of energy and how energy moves. The laws of thermodynamics are one of the few groups of principles that have reached a level in the sciences where we'll consider them to be laws of nature. There's not very many things that we can be so sure of. As we talked about earlier, so it's not that scientists are not sure about their information, but when we have theories are collections of information that we know are growing and changing as we learn more. These are what we consider to be somewhat immutable laws of nature. They don't they work everywhere. They work here, they work in space, they work everywhere. They work in nuclear reactions. And they've been in development basically since the beginning of the sciences. So you're familiar with the first one. That's the law of conservation. That's for energy, it's energy cannot be created or destroyed. Conservation also occurs for mass or matter, same thing. Well, matter is anything that has mass or takes up space, has volume. But in general, it's conservation of mass, like matter cannot be created or destroyed, and also charge. Charge will be conserved. We'll get into that when we start actually working with charge. So these are some examples I'm not sure you'll get at this point, but essentially, whenever we are using energy, we think of energy being like made in a battery. It's not made. We don't have the ability to make energy. We only have the ability to get forms of energy from existing matter. So when we're making a battery, we're just getting chemical energy out of a chemical reaction. That's what's inside the battery. We're converting stuff back and forth. So converting chemical energy into electrical energy, converting electrical energy back into chemical energy when we charge our cell phone battery. The second law of thermodynamics, my personal favorite, is all things move towards a state of increasing entropy. Entropy, I gave you kind of a bad general definition, is often described as disorder, which is a great working definition for getting you through chemistry questions, but not a great working definition to explore the deeper dynamics of what we're talking about, especially if you're going to go to higher level STEM classes. But for your purposes right now, let's just say this. Things tend to get less organized, but even if they look like they're getting more organized, as a system moves forward in nature, less efficient forms of energy are being produced. So you might start out with a super efficient form of energy like fusion energy in the sun. That then gets converted into radiant light and heat that the sun brings, radiates, and then it hits our planet. And we get that energy from the sun, and it gets converted into chemical energy by plants when they absorb sunlight. And then they use the energy from the sun to make glucose out of carbon dioxide and water. And then we eat the plants and we use a chemical reaction to break down the energy from the glucose and move it into our cells. But we also convert a lot of that energy into heat to keep our bodies warm. And so every time that that energy gets transferred to another form, it's getting less and less efficient. Okay, so systems in nature tend to have decreasing energy and increasing entropy. So less efficiency, more possibilities for no, more possibility. Yeah, more possibilities. So you have less energy, less order in many cases, but not every case. But as you move, you have basically more possibilities for forms of usable energy because you don't have a single type. You have a conversion into lots of different types. Um, this kind of goes with the existing rules that you know, right? Heat always goes from where it's warmer to where it's colder. Um, things tend to go from more ordered states to less ordered states. One of the examples that people like to use a lot, right, is like if you drop a glass, the pieces of broken glass will just shatter and spread out all over the floor. It's very unusual for the glass to reassemble itself without any input of energy, right? So that's kind of not a natural flow. And the third law, which is mostly just here for posterity, but essentially there's two ways that we think about the third law. One, if we were able to reach 0 Kelvin, which is not possible. As far as we know, we've never reached a state of 0 Kelvin, and I'm kind of hoping we don't because 0 Kelvin would be a state where there's so little energy, like all the energy would be gone and all particles would not be able to move at all. It would essentially be like the death of everything. 0 Kelvin is a theoretical kind of idea of what would happen if you took all the energy out of something. However, there are some systems that are so orderly in nature, even that we consider them to have almost zero entropy, and that would be crystalline solids. A lot of crystalline solids are really incredibly orderly, and we say that they have zero entropy. Now, enthalpy is a little bit trickier. Just think of enthalpy as us examining the overall change in how energy is moving through a system. So, a change in enthalpy is when you compare how much energy was there when you started to how much energy was there when you finished. Now, how do you make that comparison? You just subtract. It's not really scary. So, just like we did change in temperature when we did heat equations, now we're going to do change in enthalpy. And so change in enthalpy is calculated by taking the amount of energy that your products had at the end of the reaction and subtracting from it the amount of energy that your reactants had when they came into the reaction. When we do this, we call this overall thing the heat of the reaction or the change in enthalpy. They're both being the same thing. Okay, and essentially you can calculate it, but we're going to more clearly look at it on a graph together. So when you're writing change in enthalpy, you can write that as part of a chemical equation, and these are known as thermochemical equations. A thermochemical equation is just a chemical reaction where we write whether or not the energy was given off. That would be an exothermic reaction. So here you show an exothermic reaction where the heat is given off. So we make it part of the products. We write it on the right-hand side of the equation. Or we can write a thermochemical reaction for an endothermic reaction. That's a reaction where the reaction had to absorb heat in order to move forward. This happens to be the decomposition of baking soda. Had to absorb 129 kilojoules of heat, and it breaks down into sodium carbonate, water vapor, and carbon dioxide gas. Okay, so since this is endothermic, the energy is going into the reaction. It's shown on the reactant side, like all the other ingredients that are going into the reaction. All right, let's get into our graphs. All right, so very first thing, I want you to look at your graphs from a big picture point of view. Okay, on the graph, you can see on the left-hand side, hang on, I'm just going to find my stylus. Okay, I have it circled here in purple. Over here is the potential energy of your reactants or products, right? Everybody's potential energy. How much energy are you bringing to the party? Okay, over here, it says reaction progress. But you want to think of this as this is the actual reaction happening from start to finish in real time. So on the left-hand side of the graph over here, you have ingredients. Then at this point, you have the reaction happening. And then over here, the reaction's over, right? Because you have the products. So you're actually talking about the timeline of the reaction happening. All right, so now if we think about that timeline, we now have to account for whatever this means. What is this weird bump in the middle? Right? So I think it's pretty clear what these things mean. So we could draw an arrow here. This arrow represents the amount of energy that the reactants have when they come in. And then over here, if I go all the way down to the bottom, this arrow represents the amount of energy that the products have at the end. If I were to look at the graph, I'm just going to change colors, right? The difference between the energy I had when I came in and the energy I had when I left is represented by this portion of the graph. That's your heat of your reaction or your change in enthalpy. Right? So first thing you have to be able to tell is, did you end up with more energy than you came in with? Or did you end up with less energy than you came in with? So here you can see I started off with this much energy and I'm now below where I ended up. So that means I gained energy. It means I absorbed energy from my surroundings in order to use that energy to break chemical bonds or do the actual reaction. So that energy that you absorbed is now part of your products. It's stored in the chemical bonds of your products. So since that reaction absorbed energy, that's an endothermic reaction. So when you see a graph where the products are higher than the reactants, that means that that reaction absorbed energy overall, and that's an endothermic reaction. Okay, now you did an endothermic reaction in the lab. When you mixed citric acid and baking soda and your flask got cold, that's because baking soda, when it reacts, when it breaks the bond between the sodium and the hydrogen carbonate ion, it absorbs energy from its surroundings in order to do that. And so it gets cold. So that reaction is endothermic. In order for that reaction to move forward, it stole energy, heat energy from the water and used it for its chemical process in order to do that reaction. All right, let's take a look at, oh, it won't let me do it because I have annotate on. So here's a slide which goes over that, right? Where the two blue lines are, the gap between them, that represents the heat of the reaction. And the fact that the products are higher than the reactants tells you that this is an endothermic reaction. Now here is a situation where you can see that the reactants are up here and the products are down here. So I have less energy now than I had when I came in. That means I lost energy. If I gave off energy, that reaction is exothermic. Okay, and here again, you can see that change of H is the difference between the reactant energy and the product energy. The amount of energy my reactants had coming in is here. My products going out is here. All right. Now, you have to be able to read this whole graph and know what all these arrows are referring to. Now, I'm going to go over this. There's also the explanations that are embedded in the slideshow. I don't know how good my explanations were, but let's start with this exothermic reaction. All right. How do I know this reaction is exothermic? First things first is, without even really getting into it, I can tell that my products are over here, my reactants are over here. My products have a lot less energy than they did when they came in as reactants. So that means that people gave off a lot of excess energy. If they give off that energy into the surroundings, that's exothermic. They gave off heat. They released chemical energy as heat. So overall, I know that this is an exothermic reaction. Now let's go through and label all these different parts because there's another part that we need to talk about that we haven't talked about yet. And that is what this curve represents. Okay, so remember I said that this is the reaction coordinate, means that this is in real time. This is the reaction actually happening. So if you're thinking about something even just as simple as making water, right? It's not really that simple, but it's relatively simple in the big picture, I guess, right? These are individual molecules of hydrogen atoms, right? You've got hydrogen atoms plus, I'll make them a little bigger because they are oxygen atoms. Okay, and out of these atoms, you are making a water molecule, one oxygen and two hydrogens attached to it. Okay, so something is happening here, right? It's not instantaneous. It's a process, right? These bonds have to break, right? These guys can't be attached this way unless they first have to break apart. They then have to bond to each other. So one of these oxygens has to go off and make a different water molecule, and two of these hydrogens have to go to an oxygen atom to buddy up to make a water molecule. So what's being described here is this climb represents the amount of energy it takes to get from this initial energy that you have when you start the process, right? I have a certain amount of energy in my reactants. Okay, and then up here is where the magic happens, okay? Where the magic happens is that breaking of bonds and forming a new substance. You're still working with the same elements, but you're making them do a new trick, okay? So this up here where the magic happens. This is what's known as the activated complex. And how complex it is really depends on the type of chemical you're working with. Obviously, we don't think of water as being that complex. It's only 3 atoms, right? But you could be making something really complicated. And the chemical reactions required to make those really complicated big molecules could be very long and difficult, and they could require really a lot of energy to get there. So, how much energy it takes to get to the top of this hill is really what determines whether a reaction is going to happen or not. And it's kind of nice to see it drawn like this as a curve because you can think of it almost like you have to climb all the way up that hill in order to get there. Okay. So this here, this energy right here, from the place where the energy of the reactants is to the point where you get that activated complex is known as, so this is actually B. I'm moving it back underneath the hill because that's where it belongs. B is known as the activation energy. It's the amount of energy it takes to get from the amount of energy that the reactants have to the point where this reaction will actually happen. Your bonds are breaking and reforming. Okay, and then on the, so this is what I mean in the end when I say make sure you know what nonsense arrows are. I consider some of these to be nonsense arrows. First thing that I think is absolutely annoying is this little trick right here, right? Moving this arrow out from underneath the curve makes it feel not related. Also, the energy of the activated complex on its own doesn't really feel that relevant to me because it doesn't have energy on its own. It had a certain amount of energy when it came in. It had the energy that the reactants have when they come in. So I'm not sure if this is just a regions thing or if this is actually a quantity that chemists care about. C seems to represent a thing to me that is not as important, but is more like something they're just going to ask you about separately on the test, right? So C does represent the total energy that the activated complex has. However, the activated complex doesn't have that energy by itself. It really is a combination of the energy of A plus B. It really adds up to C, right? It's these two segments added together are the total energy of the activated complex. Okay, now, when you come down on the other side, here's the amount of energy your products have. And the difference between, I'm going to erase this just so I can draw a clean line. The difference between the energy I came in with and the energy I left with. Okay, an arrow that they didn't even put on this graph. This arrow, I'm going to label it E since it's not on here. This is your change in enthalpy or the heat of your reaction. Is the difference between the energy you came in with and the energy you left with. So the difference, it's the energy of the products minus the energy of the reactants. Now, notice that this number would be lower than this number, right? So let's just make up a number for a second here. I'm going to make up a number quick just so we could get a feel for how this should look. I'm going to divide the graph in half and let's just do 1, 2, 3, 4, right? Let's pretend 1 kilojoule, 2 kilojoules, 3 kilojoules, 4 kilojoules, right? If I started out with I ended with 1.5 kilojoules, but my definition of change of H says I have to do the products minus the reactants. But up here, I've got more than 3.5. Let's go 3.7 kilojoules. If I do 1.5 minus 3.7, I'm going to get a negative number. That's good. I should get a negative number because delta H is going to have to be negative for this to be an exothermic reaction, which it is. Okay, so sometimes they'll actually ask you to read numbers off the graph. Sometimes they'll ask you to sketch things on the graph, right? So like if you had to sketch, excuse me, you guys, I put this on the midterm, just FYI. If you have to sketch an exothermic reaction, all you have to do is show reactants higher than products, right? If you have to sketch an endothermic reaction, all you have to show is that your products had more energy than your reactants. You don't have to be able to show like specific numbers or anything like that. Okay, now in the back, the steps that I went over. At the end of the slideshow, I have a bunch of things, and one of the things that it's probably going to be most confusing. There's two more things we have to go over, and then I can end the video. The first one is we have to talk about the effect of a catalyst. So I know this really takes a lot of imagination, and I'm sorry for that. I'm not sure if the other video I had linked on YouTube has like a better. I wish somebody could show you a picture of this. Sometimes we can kind of spy on the atoms and actually get a sense for what those in between activated complexes look like. It's a little bit like peeking in their bedroom window and seeing what they're up to when they're in the middle of bonding, which sounds kind of dirty. But when you think about an activated complex as being like a group of atoms that are, some of them are breaking bonds, some of them are trying to make their new bonds. They're kind of in pieces and reassembling themselves like Legos, right? The order or the path they take to do that is known as a reaction pathway. And the more efficient that process becomes, the easier it is for them to break their bonds and get into their new positions and bond, the faster or more efficiently that reaction is going to happen. So it's not really about speed, but it's really about having a pathway that's efficient and makes it easier for them. Okay, and that means that I'm talking about catalysts. Okay, a lot of times I'm almost glad you guys don't remember, because a lot of times in the early days of learning about catalysts and enzymes, people will say to you over and over again, it speeds up a reaction, it speeds up a reaction. And that is actually not correct. And so as a result of that, the Regents has gone about trying to reword the questions to force you to not say that answer. And so the answer they're looking for now is that you understand that a catalyst changes, I'm going to use delta for change, the reaction pathway. Okay, one, it changes it. Two, okay, remember I said that in order to get to this magic place up here, where the activated complex is going to be and the reaction is actually going to fully start and happen. Like once you get up this hill, it's all downhill from there. It's going to be easy. The reaction started. Now you just got to roll down the hill and get to the product side. But this part over here, this is the tough part, right? You got to climb up this hill and get to the point where this activated complex is possible. Okay. So anything you can do to make this hill not so steep is going to make your reaction pathway easier. And so sometimes that will, to the observer, make it, or it will in reality make the reaction go faster. But what they're more interested in is that you understand why it's happening. It's happening for the second reason is it lowers the activation energy. Okay, so one of the other things they love to make people sketch on the Regents is they like to ask you to draw a dotted line or a second line that shows what this reaction would look like if you were using a catalyst. And what this reaction looks like if you use a catalyst is it has a lower hill. It has a lower hill. What you're not allowed to do, though, is change this or this. Okay, so here's what a catalyst does not do. A catalyst does not change the actual energy of your reactants or your products. Okay, catalysts only make the path easier. They don't change the nature of your reactants or products. Remember, they have their own amount of energy based on their own chemical bonds. So your reactants are coming in with a certain amount of energy. Once you make that product, it will have a certain amount of energy. But anything you can do to make that easier, a little online dating service there for 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 atoms, is going to change your reaction pathway. You're going to make that pathway easier. You're going to get them into the right position so that they can do what they need to do. And then that's going to lower your activation energy. So that's what a catalyst does. The second thing we have to do is we have to learn how to read this graph backwards. That sounds like a weird thing to say, but we have to talk about forward and reverse reactions. And that's because we're about to go into equilibrium land. And in equilibrium land, reactions are reversible. Not all reactions are reversible. Some are very much like to go in only one direction. And energetically, it's not very easy to get them to go backwards. But some reactions are a little more tentative and they like to swing back and forth. And these are known as equilibrium reactions. So we have to talk about reading a reaction in reverse. When you read a reaction in reverse, you turn the products into the reactants. And then the reactants become the products. And this is essentially doing a decomposition reaction, right? So like if I had a forward reaction, like hydrogen and oxygen make water, I'm not going to balance it. All right. The reverse reaction would be water breaks up into hydrogen and oxygen. Yes? Okay, you guys all know that. So that's all you're doing is you're just reading this reaction in reverse. If you read the reaction in reverse, this is the potential energy of your reactants. This line right here becomes the activation energy, the amount of energy to get from your reactants to your activated complex. Okay. This becomes the activation, the potential energy of your products. Okay. The overall reaction is now endothermic if I'm going backwards, right? Because if I'm going backwards, I'm ending up with more energy. If forward it's exo, backwards it's endo. Same thing for phase changes, right? If melting is endo, then freezing is exo. So same idea, right? What they're just reverses of each other. Where you really are going to run into trouble is if they ask you about this in a reverse reaction, because once the reactants have changed side, your activation energy starts in a different spot. However, your change of your heat of your reaction is in the exact same spot on the graph. It just changes signs. So if you're reading it forwards, it's exothermic, so it'll be negative. If you're reading it backwards, it's endothermic, so it'll be positive. Okay, so that's how you read these reactions backwards. And you're not just reading them backwards for fun. You're really discussing in terms of energy, what would it take to do the reaction to undo the reaction? Right? Now, if you have a curve like this, where you really have a very big difference in energy between your reactants and your products, you really have a much more difficult challenge on this side, right? Look how much steeper that hill is on the other side. The likelihood of this reverse reaction happening is much lower than it is over here. However, it could be done. You're just going to have a big input of energy to get it done. A lot of times, though, when we're trying to use chemical reactions to do different processes, like in an industrial process, those reverse reactions are not really very economical because you'd have to put a lot of energy into making them happen. And, energy is money. So that's kind of a problem. All right. So that's reading it backwards. That's adding a catalyst. If it was endothermic, it would just be graph in the other direction. All right, that's everything. We got through it all. Hopefully this video is not too long. It can't be more than 40 minutes because Zoom would have kicked me off. All right, I hope I didn't ramble too much. It took me about 5 times to start this. and get it done. Please make sure you go and do the Microsoft form. I did try to keep those questions in my head while I was lecturing, so I probably gave you the answers while I was lecturing. And if not, it's in the slideshow. All right. Have fun with the Microsoft form. I'll see you next week.